PGE. It's our pleasure today to have Dr. Lorena Moscardelli. Sorry.
Yeah, perfect.
I practiced it and I got it wrong. I'm so sorry.
It's perfect.
Okay. All right. I hope I get full marks for that. I'll give a little bit of background on Dr. Moscardelli before she gets started. She's a research scientist and leader in the State of Texas Advanced Resource Recovery Program, STARR program at the Bureau of Economic Geology. Her expertise is in seismic geomorphology, interpretation, sedimentology, stratigraphy, and geoscience data integration. She received a degree in geologic engineering from Central University of Venezuela, 2000, and a PhD from geologic sciences from the University of Texas at Austin. She specializes in the study of deepwater deposits with emphasis on subaqueous landslides, deepwater mixed siliclastic carbonate systems, and planetary geology. She started her career as an exploration geologist working for PDVSA, and prior to her current position at STARR, Dr. Moscardelli was a principal researcher at Equinor in industry, where she performed a wide range of activities from research in the Americas to the field development in Norwegian continental shelf. Her BEG career also includes co-founding and co-directing the Quantitative Clastic Laboratory and her actual involvement as the leader of STARR. Most recently, Dr. Moscardelli has taken a strong interest in understanding the roles of geoscience research as part of the ongoing energy transition, while contributing to STARR's main mission of conducting geologic research, resulting in increased production profitability for energy resources in the state of Texas. Dr. Moscardelli, thank you so much for joining us. The floor is now yours.
Thank you, Michael, for the kind introduction and for the invitation. It's a real pleasure to be here. As mentioned, I'm a research scientist at the Bureau of Economic Geology and the principal investigator of the State of Texas Advanced Resource Recovery Program, also known as STARR. I want to start by highlighting that when it comes to hydrogen, we're working in close collaboration with several research groups, including the Applied Geodynamics Laboratory at BEG, and also members of the Petroleum Engineering Department, many of whom I see here today. We're in early stages, but I think we're learning tons, and I'm very excited about that. My objectives today with this talk are to first introduce you to the STARR program at BEG. Second, to share some of my views regarding the energy transition, hydrogen, and our role on it as geoscientists and engineers. And finally, to show some updates on the research that STARR is currently pursuing regarding hydrogen. And please keep in mind, we are on an early stage, but we think we are pursuing the right questions and making good progress. And hopefully we will have some time to have a nice conversation towards the end. Before we start addressing hydrogen, let me introduce our program. The mission of the STARR program is to conduct geoscience and engineering research to increase the production and profitability of earth resources, including oil, natural gas, hydrogen, geothermal, and minerals, within the state of Texas, while encouraging responsible economic development and supporting education and environmental stewardship. STARR is funded by the state of Texas, and our team performs research on a variety of topics that are important for the great state of Texas, including water resources, mineral and earth resources, energy, land resources, geohazards, and special projects. Today, I will be talking about one of our STARR special projects regarding hydrogen storage in Texas that falls into the broader theme of energy. This is the structure of the STARR Energy program. I'm not going to spend too much time on this slide, but we have three main components: the geoscience corner with regional studies and lots of one-on-one interactions with Texas operators, the engineering component led by Ian Duncan, and where a wide range of research activities linked to improve oil recovery strategies and hydrogen are taking place. Worth mentioning here that there is a lot of great interactions and collaborations between STARR engineers and the Petroleum Engineering Department here at the UT, so that's great. And finally, we have our hydrogen storage in salt formations, a scoping project that is currently a STARR special project. So we do a lot of stuff all over the place. This is part of the team, a wide variety of expertise levels, from senior research scientists to graduate students working on a broad range of problems in the geoscience and engineering, from the micro scale with the studies on pore media to basin scale geological characterization projects. So it's a great team that works very well together. Now that I have introduced the STARR program and you know where to find us, let's start talking about the energy transition and the why this is important. Having context today is more important than ever, I think. So I stole this graph from Philip Ringrose, one of his latest presentations that you can find online, and you can see years on the x-axis and global emissions of CO2 in gigatons. Now that, when we look at this, we need to think about CO2 anthropogenic emissions to the atmosphere, and to realize that there has been a rise since inception of the combustion engine and the subsequent start of the industrial age. But we have seen an important increase in CO2 emissions as we started to use hydrocarbons to fuel our society or progress and to fulfill the needs imposed by our lifestyle. So CO2 emissions have really skyrocketed over the years. The impact that CO2 emissions have on climate change and global warming is a subject of polarizing opinions. I personally believe that scientific evidence shows that anthropogenic emissions of CO2 have a negative impact in our environment. But there are many who question this assertion. This talk is not about that today. But regardless of your position on this, the reality is that the so-called energy transition is here to stay. So I have been wondering for a while, what's the role of geoscientists and engineers working in the oil and gas industry as part of this transition? Well, first thing to notice is that the oil and gas industry has, as we knew it, is gone. And now there is a rebranding into the energy industry. I don't really have a clear answer to these questions, but I have two comments or two observations. The first one is that when we're talking about energy transition, we really need to pause and think about the definition of transition, which is a process that requires time, where we're going to change from one state or condition to another. So this is going to take effort and time. The second comment that I have on this is that I believe that oil and gas still will play an important role during this transition. And at the same time, many other technical challenges, like the challenges that we have when it comes to hydrogen, are arising. And this is a good thing for engineers and for geoscientists. So I see this challenge as an opportunity. In 1865, Jules Verne envisioned a projectile that would take men to the moon. And then on September 12, 1962, then President Kennedy said, we choose to go to the moon in this decade and do other things, not because these things are easy, but because these are hard. On July 20, 1969, Neil Armstrong took a small step for man, but a giant leap for mankind. The rest is history. So what's the point of me making this analogy during this talk? I find it fascinating that a French novelist and poet who was born in 1828 could envision so many things. It was 1875, same guy published The Mysterious Island, where he envisioned this concept in which one day water could be employed as a fuel, a concept in which hydrogen and oxygen, combined or alone, could be used as an energy source. I guess I don't need to tell you about the news, the headlines, and Washington these days, but I wonder, what if, why not? The concept of decarbonization of industrial clusters is not new, and countries and companies are already investing billions of dollars on these endeavors. Here, just mentioning two examples, with Equinor partnership with Engie in the UK to use blue hydrogen in the Humber region. Another example with Shell, recently opening the largest PEM electrolyzer in Europe. So this is happening. Is it going to be enough to take care of the energy demands in Europe in the short term? I don't know. We will have to see. But plans and investments are certainly ongoing. Here it comes hydrogen. Hydrogen can be used as an energy carrier, and this is important. Hydrogen is not an energy source per se. It's a carrier that allows us to transport and store energy. That's the beauty of it. It's the lightest element in the periodic table, colorless, odorless, non-toxic, highly combustible, non-metallic. Hydrogen is the most abundant chemical substance in the universe, constituting roughly 75% of all normal matter. Most of the hydrogen on Earth exists in molecular forms such as water and organic compounds, including hydrocarbons. And here's where the challenge comes. I cannot use the water molecule as an energy carrier or as an energy source. I need to break it. So we need to break hydrogen, we need to be able to transport it, and we need to be able to store it. So these are the challenges that we have in front of us. I also stole this nice slide from Philip Ringrose to illustrate that the use of hydrogen as an energy carrier is particularly important when we are talking about heavy industries such as steel and cement, as well as long-distance transportation. So if we really want to decrease CO2 emissions, hydrogen is our best shot. Not all hydrogen is created equal, and there is a plethora of colorful designations, but three colors are to be remembered. Gray hydrogen refers to the production of hydrogen via steam methane reforming, where the input is natural gas and the output hydrogen and CO2 emissions to the atmosphere. Blue hydrogen is also produced via steam methane reforming, but the resulting CO2 is captured and sequestered in the subsurface. Finally, green hydrogen is produced from water via electrolysis that is powered by renewable energy, either wind or solar power. The challenge with green hydrogen is that electrolysis is not a cheap process today, and water can be a scarce resource. When it comes to renewable energy, we have all probably heard that the sun doesn't always shine and the wind doesn't always blow. However, sometimes the sun is shining and the wind is blowing when demand is low and capacity generation is high. And this is expensive, given that there is a dollar amount to turn off generation capacity on a wind farm, for example. The graph on the slide shows the curtailment of wind power in green within the UK and associated constraint payments in yellow made by the UK government from 2012 to 2020, including projections to 2030. In 2020 alone, the rejection of 3.7 terawatt hours from the system cost £274 million, with projections for 2030 that double this cost. Wouldn't it be great if this excess capacity could be somehow stored into a battery for later use? This graph shows several energy storage options that highlight in the x-axis storage capacity versus discharge time. Storage options that involve subsurface geological options are highlighted in blue, and you can see that these are the ones that can store more power and deliver for longer periods of time if needed. This illustration to the left shows potential hydrogen storage solutions, including depleted hydrocarbon reservoirs, aquifers, and salt domes. From these three options, salt caverns are a proven concept, but upscaling of hydrogen storage in salt caverns will require additional research, including a better understanding of salt cavern feasibility in offshore salt bodies. In other words, a potential solution for subsea hydrogen storage. The table to the right shows the 4 hydrogen storage locations associated with salt formations today. 3 within salt domes in the Texas Gulf Coast and 1 within layer salt in the UK. Spindletop is the largest, with around 8,000 tons of hydrogen storage capacity that is equivalent to 274 gigawatts hours of net energy stored. The UK numbers have been updated since 2015, and today hydrogen storage capacity in this facility has increased to 1,000 tons from around 800 tons in 2015. This is equivalent to 33.3 gigawatt hours of net energy stored, meaning that 454 equally sized facilities will be required to deliver net zero carbon emissions by 2050, according to this work by Wallace and collaborators. That's a lot, it's epic. From all these storage options, salt caverns are a proven concept, and because of time, I will talk about salt domes as hydrogen storage options during the rest of the talk this afternoon. So what is a salt dome and what is a salt cavern? A salt dome is a dome-shaped structure formed where a large mass of salt rose up as part of a sedimentary succession. A single salt dome can host several salt caverns. Hydrogen storage in salt caverns, as I said, is a proven concept. with at least 3 salt domes storing hydrogen today in the Texas Gulf Coast and 1 small cavern field storing hydrogen within layer salt in the UK. The average height of a salt cavern is around 2,000 feet, and its average diameter is around 200 feet. Even though salt domes in the Gulf Coast are very common, not all salt formations are created equal. Some salt formations are more complex, presenting a great deal of internal variability and impurities that can go from chunks of deformed rocks to fluid inclusions inside the salt body. Understanding this level of complexity is crucial for the placement of salt caverns. There are no salt caverns storing hydrogen within this type of complex salt formations in the US. However, there is storage potential here if we manage to better understand the geology of these units and the nature of the interaction between hydrogen and layer salt. I'm showing in this slide Texas as a case study where abundant and reliable natural gas supply in the Gulf Coast, existing hydrogen infrastructure and storage, as well as potential for carbon capture and sequestration, flags this region as prime real estate to develop a hydrogen economy that can supply not only the petrochemical industry, but also refineries, the transportation sector, and other industries. In West Texas, the potential of wind and solar energy in conjunction to the presence of both layer salt formations that could be targeted for hydrogen storage and CCS potential makes this region an option to manage large-scale storage seasonal challenges associated with solar and wind via hydrogen storage solutions. We still need to assess potential and study feasibility, but it is an option worth exploring, I think. The concept of salt caverns is not new, as I said, by any means. In fact, salt brining in East Texas began in 1904. Salt caverns have been used for multiple purposes, including waste disposal from oil and gas operations and hydrocarbon storage, among other purposes. The most popular user of salt caverns in the United States is the US Strategic Petroleum Reserve. I think there was mention of them in the news today. There are 4 salt cavern fields in the Gulf Coast region, hosting a total of 60 caverns with a storage capacity of around 700 million barrels of oil. This map in here, this is plan view, shows the contours of a salt dome and the location of multiple salt caverns in green. These seismic sections in here to the right show vertical profiles similar to an X-ray of a salt dome, giving you an idea of how these salt domes look like in the subsurface. So essentially, the salt caverns are placed inside these units. Salt formations are abundant. In Europe, the highest density of salt caverns are located within Paleozoic salt deposits to the north, but the potential of younger Mesozoic salt formations in southern Europe seems to be underexplored. In fact, in Spain, there is a project called El Valle del Hidrógeno, the Hydrogen Valley, who is actually looking at these very actively. In North America, salt formations are also abundant. In Texas, salt domes are prevalent in the Gulf Coast, where hydrogen storage is already ongoing and natural gas supply is abundant. On the other hand, more complex layer salt is present in West Texas, where the concept of hydrogen storage within salt caverns has not been proven, but where potential for wind and solar energy is high. So we need to look at these more closely. It looks like the Gulf Coast would be the low-hanging fruit to a relatively quick monetization of investments linked to hydrogen storage. We have a steady supply of natural gas and existing hydrogen pipeline infrastructure shown in blue in the map, steam methane reformers, proven hydrogen storage concepts shown in the map by the red circles that represent the location of some of the salt domes that are common in this region, clear CCS potential given the thick sedimentary sequences in the region and the pilot studies that have already demonstrated that it is feasible to sequester CO2 in here. So then what is not to like about it, right? However, if we want to increase the number of salt caverns in this region, then we need to engage in additional research to help us maximize salt cavern placement. For example, how to predict weak zones within salt domes is a big research question that remains unanswered. This is important because these weak zones can compromise the integrity of infrastructure by deforming well casings as well as causing the collapse of the caverns. Geoscientists and engineers are particularly well positioned to help answer these questions. To the upper right of this slide, you can see a numerical model that simulates the formation of a salt dome, similar to the ones that are present in the Texas Gulf Coast. Red colors in the animation show areas of rapid salt movement compared to the blue background that represents slower moving salt. The boundary between rapidly moving salt in red and slower flow in blue can define areas of weakness that we want to avoid when planning salt caverns. The figure to the lower right is a physical model of a salt dome, also showing complexities of salt movement using passive markers. Predictions of these weak zones can be improved by using these methods, and expertise from salt tectonic experts like the ones in the Bureau will play a crucial role in advancing our understanding of these issues. Worth mentioning our ongoing collaborations with AGL, the salt experts at BEG, and many others who are helping us frame the research questions that we need to answer in years to come. So there are many research questions that still need answering, and among them, what is the origin of methane contamination of stored hydrogen? This is something that I have heard has been reported by some operators. Is this contamination coming from gas inclusions within the salt body? Are there shear zones or weak zones connecting active petroleum systems in the surrounding areas of the salt domes to the caverns? And most importantly, what are the mitigation measures to avoid or remediate methane contamination? Do we need to avoid active petroleum systems in surrounding areas, which would be very difficult in the Gulf Coast, for instance, or the Permian Basin? Are there any engineering solutions? How do we understand this problem better? These are just some thoughts, and there is more, a whole lot more that needs to be investigated, but just trying to give you a taste of where we're going with our ideas here. As we move forward in the energy transition and as the hydrogen economy evolves, we will need increased hydrogen storage capacity, and storage in salt formations won't be enough. However, extensive research and testing will be needed to fully understand the feasibility of hydrogen storage in pore media, either aquifers or depleted reservoirs or both. Areas of research include the implementation of numerical models that can help us better understand thermodynamic, hydrodynamic, geomechanical, and biogeochemical processes that can govern the interaction of hydrogen with pore media. This needs to go hand in hand with the geological characterization of these potential storage formations, including the study, the old-fashioned study, I have to say, of core, for instance, or seismic studies. So this is not going to be easy, it's not going to go fast, and it's going to be expensive, which brings me back to the transition part of the energy transition. We're going to need to put a lot of resources into this and a lot of intention to solve these problems. This is my final slide, and I just want to show here some of the ongoing research initiatives by our STARR engineers. To the left, modeling efforts by Bo Ren, who I think is in the call, that show hydrogen versus CO2 flow in a storage aquifer. We can clearly see that hydrogen and CO2 behave very differently with faster upward migration of hydrogen. These observations, of course, have implications in terms of leakage and fingering. I'm really looking forward to see what Bo will develop in the future in this line of research, because it's going to be very important. To the right, some ideas and concepts considering in situ generation of hydrogen within depleted reservoirs. Ian Duncan and collaborators are actively working on this concept, a concept that could potentially address concerns associated with both methane and CO2 emissions associated with the generation of blue hydrogen, because essentially you are managing the process within the reservoir. So some conclusions and highlights. There are a bunch of salt domes in the Texas Gulf Coast that can provide feasible hydrogen storage options. There are certain parameters, and we're currently working on defining those parameters and updating a catalog for the Gulf Coast. Many of these domes are close to relevant infrastructure and access to market, a market that is still evolving and developing. But this will help with quick monetization while accelerating energy transition goals. And that's why I talk about salt dome real estate, because as soon as we start to understand this better, then some patterns will start to arise. Research is needed to better predict optimal position of salt caverns and to optimize salt dome real estate, even though this concept is proven, hydrogen storage and salt caverns. If we're going to increase the volume of storage, we're going to be required to place those caverns and to create those caverns very efficiently. And there are many outstanding questions that we still need to answer, including, is it possible to store hydrogen on bedded salt in the Permian, for example. Research is also needed to better understand hydrogen storage potential in offshore salt domes. This is very interesting, something that I'm very curious about, because there are great deal of investments in offshore wind, especially in floating technology. And, the question is, what are you going to do with that excess capacity when it arises? Are you going to try to do some kind of hydrogen? And then what do you do with it, right? So these are all interesting questions. Finally, West Texas layer salt formations are prime targets to evaluate the feasibility of green hydrogen storage to mitigate seasonality of wind and solar energy. And we're starting to formulate questions and plans that will allow us to answer some of these questions. So I think it has been roughly half an hour of me talking. And with that, I'm going to stop it and open up for comments or questions. I think Borren, Frank Mel are also in the audience. So when the engineering questions arrive, I'll skillfully divert to the real engineers in the audience.
Thank you very much, Dr. Moscardelli. That was awesome. I really appreciate the message around hydrogen opportunities in the subsurface. I want to give an opportunity to students, graduate students, undergraduate students to ask questions. Go ahead, you can unmute yourself.
They're shy.
I know. Any students want to ask a question? All right.
Maybe I should ask the questions. You tell me the name of the students and I'll call them and ask. No, I'm joking. There is something on the chat. Huh?
Yeah. Oh, is there something on the chat? No.
Oh, Larry Lake. Thank you, Larry.
Hi, this is Tarek Mohammed. I'm a second year PhD student. So I'm on. So I have a question. I see that the biggest challenge you're focusing on is storage. What about the water needed for generating? Because we know that until now it's only fresh water that's needed, and it's places in the world they have drought already. So the fresh water for drinking is more important than having clean energy, I think.
Yeah, no, I agree with you. I mean, talking about water, I would prefer to have water than hydrogen in my glass. But that's a very good question that you're posing, particularly, I think, within the context of the talk in Europe. In Europe, if you talk about blue hydrogen, you're a sinner almost, because it's perceived to be as also polluting, But I don't have an answer for you other than to tell you that it's going to be a huge challenge because water resources are not a trivial thing. And for instance, when we talk about West Texas, we know that we have excess or potential for excess capacity for wind and solar. So in theory, we would have the energy that is needed for electrolysis. But that's a good question. Where are we going to get the water from? And I think here is where we need to start to look at water budgets and start to put our act together. The Bureau, for instance, this is an advertisement, I guess, but we have a strong environmental group that has been for years working on water resources. So one exercise that I would love to engage with is to see in terms of volumes, how would that look like? And can we do it? Offshore, do we need if you think about, okay, let's think about offshore wind. There's plenty of water in the oceans, it has salt. So I think you need fresh water for most of these electrolysis processes. How are you going to manage that? Is it feasible? What are the timelines? I think there is a solution for every problem, right? That's what engineers do. And history has shown that with enough time, resources, and thought, you can find a solution to these problems. But right now, I don't think there's an easy answer for that.
Thank you.
Any other questions from students? All right, I'm not going to hold back faculty any longer. Any questions from anyone on the call?
Now the scary part comes.
Dr. Mohanty. I see your hand up. Did you want to ask a question? Okay, maybe Dr. Mohanty is not on right now, or Dr. DiCarlo. Oh, Mohanty.
Yes. Okay, I unmuted myself. I was asking the question without unmuting. Thank you for a very nice talk. I want to ask you, if we take the hydrogen from the solar and wind, what's the time scale? What's the volume scale? Because these are going to be important in determining what kind of storage we need.
Yeah, that's a very good question. And, you know, the economists at the Bureau are working on that. But what I'm doing in my very humble geoscience hat, when you start to read about it, you start to grasp the magnitude of the problem at hand. And that's why I want to say, especially to students, that I feel confident that there is going to be a job market for us in the long term. I'll just mention these numbers that I found. I don't have a good picture for you for Texas or globally, but I think the magnitude of the problem is more or less the same. I was mentioning this, but I guess I went through this slide very quickly. In the UK, the current storage capacity of natural gas is more or less equivalent to 16 terawatt hours of power, stored power, which would be more or less equivalent to 6 days of average demand in the UK. They have one hydrogen storage facility in the UK, and it can store around 1,000 tons of hydrogen that, according to these guys, is more or less equivalent to 0.33 terawatt hours of power. So, you know, if you want to replicate these 6 days of average demand, you will have to add an additional 232% of hydrogen volumetric capacity. You know, I mean, it's massive. And I think the number is like 400 something additional, 454 facilities like the one that is currently in use. That's a lot. So, and even this number, there is another interesting thing that happened here. Because if you look in the news, not long ago, there was this storage facility of natural gas in offshore UK that was decommissioned. And it was 70% of the total store capacity of natural gas in the UK. So 6 days is not too much either, right? So again, take this comment from a geologist. I'm humble, but I think the numbers are going to be epic.
Thank you.
Dr. Mohanty, did you have a follow-up question?
No, that's all right. I've got a lot of other hands.
All right, thank you very much. Dr. DiCarlo, a question?
Well, thanks for the talk. Yeah, I have a question also about these timescales. So you mentioned in your last slide, it was seasonal storage, kind of like you want to seasonally store natural gas, or is it more for basically the diurnal storage for the solar and wind peaks during the day?
Yeah, The latest. I mean, I
Is
think
it A or B or a little A or a little B or what?
I think for hydrogen, the idea is to take the low demand in electricity and high peaks of wind or solar generation and use that excess capacity to feed the electrolyzers that will, you know, get your hydrogen then for storage. And then you store the hydrogen. I think that's the basic premise. And once the hydrogen is stored, then you will be able to go there and get the hydrogen when you need it, which is quote unquote, because I'm also starting to learn that your injection withdrawal cycles, you're also dependent on that. It's not like you can switch and it's going to happen immediately, right? So the engineering behind that is quite complicated.
Well, I guess I'm talking about the time scale. Is this for the seasonal or is it for the daily?
I think that the graphs that I have seen, they show the daily ones, but I think it also changes through the year, right? So like, I'm unsure. That would be the answer.
Yeah, because it's totally different things that are needed, right?
Yeah.
Store natural gas seasonally now and daily, but mainly seasonal. That's what you have here for the UK data. Basically, they put it away in the spring and the fall to use in the summer and the winter as needed. So I mean, I know that the round trip cycle, you lose 70% of the energy when you take the energy and move it into hydrogen, move it back. We only lose about 20% on a battery. But it has the opportunity, you can put a lot more away. And that it might scale better when you build big, you don't have to build, when you build the big salt domes, or they'd be big enough to, yeah, you have this plot here, which I find, okay, fascinating here.
It's a matter of scale.
Yeah, so it's big for the days, not the hours. That looks like it's the biggest.
Yeah.
Okay, so seasonal then rather than diurnal.
Yeah.
Okay. Thank you.
Dr. Delshad, do you have a question?
Yes, thank you so much. What a informative talk. Thank you again. So my question is more general. One of the issues we have today with hydrogen is the cost. And it's not going to become to the scale that we're interested unless we become competitive with other energy sources. And Department of Energy has a program so-called 111. For those who may not be familiar, one is so the target is really $1 per 1 kilogram of hydrogen in 1 decade. So what is your opinion? Is this really achievable with what we know today? If not, is it going to be $2 per kilogram? What do you think?
That's a difficult. Are we recording this? Well, the other interesting thing is you said kilogram. You're talking about kilogram of hydrogen, which I mean, my understanding is that the energy density there is a whole lot higher when we're talking about mass versus the gas. I see it as an uphill challenge to get to those numbers, to be honest. Especially in the US, because if we, I mean, the way European research work is quite different than in the US, even though there is a lot of money in here. You know, what I'm seeing right now is that European governments are really investing a whole lot of money into trying to ramp up this. So I don't know. I don't have an answer for that. I think it's very challenging, and it will depend on the amount of money and effort that we put into it. But I think in a 10-year time frame, we will definitely see important advances and changes. I don't know if we're going to be where we want to be or where the ambition is, But I think we're going to be in a different place than we are today, and probably for good reasons, you know.
But so do you think, like, you know, among all the rainbow colors that you showed for hydrogen, potentially blue hydrogen combined with CCUS has a better chance?
I don't think I mean, this one I can tell, and that's an opinion also that I have for Europe. I don't think green hydrogen will do it in 10 years. I think we definitely need blue hydrogen as part of that transition. For a situation of cost, we have the technology for this. We know we can make this happen. You know, of course, it needs tweaking and it needs improvement, but we can do it at a reasonable price tag, you know, I think, or something that is ambitious but doable. The green hydrogen, I don't see it as a short-term solution, definitely not.
Okay, thank you.
Dr. Ravikumar, do you have a question?
Yes, thanks, Michael, and thanks for the great talk. I wanted to follow up with Professor Delshad's question, actually. You know, if we assume, you know, we achieve DOE's target of $1 per kilogram of hydrogen production, one of the slides you said you showed said storage costs of the same order of magnitude, $1 per kilogram of hydrogen. Given that, you know, the production and the storage costs are actually comparable, do you know if there's been any analysis done of the spatial distribution and optimization of a hydrogen economy? Speaking basically about, you know, hydrogen production, storage and transport, and hydrogen use in various demand sectors. Has there been an analysis of where would be most beneficial to site such storage, given what we know about the cost of production and the need for hydrogen in demand sectors?
I think we're all trying to figure that out. And I know, I mean, there is this joint effort actually with the Petroleum Engineering Department and the Bureau on this GeoH2 consortium, where we have our chief economist and many other people, some of them in this call, trying to figure that out. So I cannot give you a number or cite a study to provide that answer. I guess my gut feeling is the same gut feeling that most of us would have. In terms of the US, I can clearly see the Gulf Coast as a hub for this, because most of your refineries are there. You have ports for exports. You have major urban areas that would benefit from electricity generated via hydrogen. West Texas, I don't know, that's a question mark. Maybe if we think about the electrification of oil and gas infrastructure in West Texas, as Norway did with the electrification of offshore infrastructure, where they take hydropower and they take the electricity onshore, offshore to power the platforms. Can we do that here? Do we want to do that here? Does it make sense to do it? Then you have the Northeast. I know there are big conglomerates of steel in there. There are salt formations in there. There are, you know, aquifers. So maybe thinking about those industrial clusters where the need and the demand for electricity is high, could be, you know, an option. But this is me telling you an opinion. I'm not really sure about how that looks in paper and the numbers, you know.
Dr. Livesky, do you have a question?
Yes. Thank you very much, Lorena. Great talk. I would like to follow up on David's question, actually. So, you know, in my previous life with Baker Hughes, I was involved the project, the salt cavern you show, Moss Bluff in Texas. We install an optical fiber in that injection well and monitor the temperature. But my question is regarding the efficiency of the system. So apart from the efficiency of the storage storing cycle, in days or weeks or whatever. Do you have any information actually about how much hydrogen is lost during, the cycle in a salt cavern or in any kind of underground storage actually facility?
I don't have the numbers, and to be honest, I don't have an informed answer on that. I think someone mentioned here 70%, and I was like, what?
But is that based on the mass of hydrogen lost, or is that because of the energy conversion, cycle? David is making a sign.
If I may, I don't mean to, that number came from, I just looked up as a paper by a couple authors. It's basically the conversions. It's not any loss. It's just how it takes to convert and then pump it down and then produce back up is generally about 70% loss.
I know there are some studies because there have been attempts to also store hydrogen, not as pure hydrogen, but these mixtures on porous media. So there are, I think the other day I was looking, and there is documentation in like aquifers or depleted reservoirs of hydrogen loss. But in that case, they were talking about interactions with bacteria. That's the other problem with hydrogen, that is very reactive to certain minerals and certain conditions on the subsurface. And actually, those numbers that I saw were not that great, because they lost a lot of the hydrogen. So how to mitigate that? It's unclear to me. And then the other thing is, like, okay, let's say we figure out the hydrogen storage on caverns, including bedded salt, which is very challenging. But if the hydrogen, we figure out the hydrogen economy and all this stuff, we're not going to have enough storage capacity only on salt formations. One, because of geography. I mean, salt is not all over the place. That's one thing. Second, volume. I mean, at some point you're going to run out of space. So then what we're going to do, and I think in terms of the research, it is true that the research potential and opportunities on the porous media, I think are huge, probably higher than on salt. Even though there are things in salt that we need to figure out, there are more questions that need to be addressed when we think about potential in aquifers and depleted reservoirs. So as I said, I'm an optimist. I see cows as an opportunity. Plenty of work to do. We just need the money to do it, right?
All right, thank you, Lorena.
Professor Perdonovich, did you have a question?
Yes, so just to interrogate a little bit on salt caverns. Well, I know with the nuclear waste storage, the problem is if the temperature rises, which could potentially melt some of the salt, open it up, and if salt gets in contact with water. But with hydrogen, presumably we don't have that problem. Is that correct?
It depends on the type of salt. And this is where that's why you engineers need geologists, and we're happy to work with you because, for instance, in the Gulf Coast, the good thing is that you have these salt domes, as I show in the picture somewhere.
Yeah. How fast do they move, or how much do they move per?
No, they
is that a problem on the time scale that we need them?
No, they form. I mean, the whole thing forms under millions of years, right? So that's a different scale. Some considerations that you have to have in here is that I think the caverns need to be placed at certain depth ranges, like it cannot be deeper than 2,000 feet to avoid creep, or you need certain amount of overburden, right, on there. But the problem for salt cavern, even though there can be complexities in here that I think still need to be explored, in the scale of difficult to easy, this is easiest, to handle. But if we think about West Texas, for instance, they have bedded salt, and in there the mineral composition is not uniform, and you also have impurities in there. And then the problem there is you can have the hydrogen reacting with anhydrite, for instance, and that's not a good thing because you can generate sulfur. So these are the kind of things that we need to better understand. As I mentioned earlier, we're in early stages. I'm also learning myself. What are the
stupid
criteria?
Follow-up question. I mean, this cavern, you simply dig a cavern, but presumably you could cement it up or create a bunker of sort in that salt. Is that a possibility or not at all?
I think they create this by the dissolution. So they inject fresh water, and then, so that's another problem with water management. In some bedded salt formations, I think they have engineered the caverns. Either they can put like, you know, they can put stuff on the walls to try to conceal, but that's extremely expensive.
Okay.
So it's not a, yeah, it's not an option.
You can reinforce it somehow. Okay, thank you.
Yeah, no problem.
And Professor Delshad.
Lorena, I just want to comment regarding the last question regarding the loss of hydrogen.
Yeah.
During the geologic, we've done some, I'm sure you've seen some of my talk. I've done some numerical simulations of hydrogen injection in depleted oil and gas that was used to as a gas storage site, and also 2 saline aquifers. So again, these are just numerical modeling, but I had a good idea about the subsurface, you know, heterogeneity and characterization. Based on our numerical simulations of multiple cycles of hydrogen for seasonal storage, we ended up with about anywhere from 40 to 50% loss of hydrogen, like as a cushion gas. And I think that's one of the reasons there are a lot of groups that they're thinking about using another gas as cushion gas, like nitrogen.
Like nitrogen, yeah.
But so now I'm really, I don't have the answer to this question. I hope maybe you do. That what is going to happen if I start with injecting nitrogen first and then add hydrogen? Then what is going to happen on the production side? That I'm still going to potentially produce mix of gases. And is that going to create a concern, or for transport, for separation, or is not going to be a big deal?
I don't know that, but first comment, I have seen your models, and those are, if you guys haven't seen it, it's fascinating, because also the way the diffusivity of hydrogen compares to other gases, it's mind-blowing. Now, I have read that they were talking about nitrogen to replace potentially natural gas as cushion gas, also because of a cost perspective. I guess nitrogen would be cheaper. But what would be the impact on that? I really am not qualified at this stage to comment. Now, in the producing gas, or whatever you withdraw, the one thing that I know, because I have heard this from people, is that if you're talking about fuel cells, you really need pure hydrogen. So
yeah, that's correct. For that, you cannot have any impurity in hydrogen.
So that's why I'm saying that I think it's accurate to think that the big role of hydrogen within the context of this energy transition is not to use for fuel cells for cars, electric cars or whatever, but for big industry, you know, where essentially you don't need that level of purity to get the power you need for the cement plant or whatever, you know. But I mean, other than that, I really don't have more info or insights.
No, thank you very much.
Any other questions? All right, this is a great discussion. Thank you very much, Dr. Moscardelli. I got to tell you, it really encourages me. I just realized that the subsurface engineering and geoscience remains critical in the energy transition.
I think we are living special times where a lot of the message to our students in the geosciences and in the engineering, especially those working on petroleum geoscience or petroleum engineering is that, wow, this is the end of the rope here. And contrary to that, I think there are many challenges, many opportunities where the expertise that we bring will be critical if we're going to really move forward into this. So I hope I can leave you with at least my optimism that we still have a role in the energy transition.
Thank you very much. Appreciate it.
Thank you, guys. All right, Michael and everybody, thank you very much.
Hey, let us know when you're on the 40 acres. Got to drop by for a coffee.
Definitely, I'll send you. I'm going once a week at least, I think. So I'll let you know and see if we can have a coffee. That would be great.
I also need to make a trip. I haven't been to the Bureau in a little bit. I need to come visit the Pickle campus and see the Bureau.
You're welcome.